Okay, so today we're covering Module 7, Inquiry Question 3. And in this inquiry question, we're looking at the quantum model of light, which means what evidence are we looking at that supports the particle-like nature of light, and how's that changed our understanding of physics, and how have we come up with this idea of the quantum model? The inquiry question we're going to investigate is the evidence from the photoelectric effect. So we're going to look at what the photoelectric effect tells us. That demonstrates inconsistencies with the wave model of light. Okay, so that's the first thing we need to look at. The second part will be to look at what the photoelectric effect tells us in terms of the law of conservation of energy and then the photon model of light. So we're going to try and connect all these puzzles together. All right. So let's start off with a quick diagram to show for the wave model of light. Now, imagine you have a surfing wave of water and it's coming towards, the coastal line. Now, we obviously associate a high amplitude, so a high displacement or big displacement of a wave. We usually relate that to its overall kinetic energy. So the higher the displacement or the greater the intensity of that particular wave, the more energy we associate with it. If we have a low amplitude, so a low displacement, that means the intensity of the wave is low, and we tend to associate that with low kinetic energy. Now we're going to look at why this is not going to be consistent with what we see with the photoelectric effect. Just to get ourselves started, to really define what the photoelectric effect here is, on the right hand side, so this side here, this is a display of the photoelectric effect. If you have photons, photons is just another word we use for light, but we mean light particles sometimes. The photoelectric effect essentially states that when a photon strikes the surface of a metal, you'll make an electron come out. Okay? Now, obviously, as you can see on this side, we also have photons. We're also firing it on the surface, but we get no electrons coming out. They are stuck on the surface of that piece of metal. So why is that the case? How's that not consistent with the wave bond of light? That's what we're going to look at. Okay, but firstly, let's look at some investigations of the photoelectric effect and see what that's taught us about some inconsistencies with the wave model. Now, I'm sure you remember this person here, Heinrich Hertz, the guy who discovered radio waves. Remember, he used a high or AC voltage source to oscillate a charge, and that produced radio waves. If you also remember, those radio waves would hit a conducting device, a conductive loop, and that caused sparking. Now, that sparking is caused because there is a displacement of electrons along there. So what you're actually witnessing when he did that initial investigation was the photoelectric effect. You have some kind of radiation or photons colliding with a piece of metal and making those electrons jump from one surface to another, partial, but nonetheless, that's how it works. I did a couple of follow-up experiments, nothing really big, so he didn't really put a big contribution here. He just did some experiments here and there. He placed a block of glass between the radio waves and the conductive loop. And what he found was the sparks would still go on at a more diminished level, but it showed one thing, that radiation could go through non-conducting materials. Okay, so that's an important finding there that we know of. Another thing we could look at is another follow-up experiment he did. He decided to shine ultraviolet light onto the conductive loop. And when he repeated the experiment again, after this circular loop was exposed to ultraviolet light, he found that there was a greater or an increase in spark. So there was an increase in sparking, which means that there were more electrons displaced. He also did another one. He used quartz, which basically blocks off, or doesn't block any UV light. What he also found was once the quartz was used, the spark went back to the original spark level that he had when he first started the experiment. So these were some of the things he saw of the photoelectric effect, but he never actually made any further investigations afterwards. He just wrote it down, and other people end up having a look at it afterwards there. Okay, so let's look at some of the findings he looked at. Okay, and let's just redefine the photoelectric effect. So the photoelectric effect is the emission of electrons from the surface of a conductor when subjected to electromagnetic radiation of a particular frequency. So this term here that we have of a particular frequency, that's going to be the defining factor that will suggest some inconsistencies with our wave model. So when the receiver is enclosed in a dark box, the spark would diminish because it blocks off UV light. The box was replaced with quartz and sparking remained the same. And a mercury vapor lamp, that's usually a good emitter of UV light, increased the level of sparking. So what does this tell us about the photoelectric effect? Well, firstly, he didn't actually do much along the lines of that, but there was a man that would later on pick up on his work. His name is called Max Planck, and he came up with this famous equation, the quantum equation for the energy of light. So let's have a look. First thing, one of the simple demonstration, you will have an electrode, and think about it this way. Say we have two metal pieces lined up like so, and you charge it up. So, with static friction, you charge it up with a metal rod. That metal rod will inflict, let's say, negative charges. Let's just use negative charges in this example, and it makes the whole metal piece negative. Now, what we know is when you have two sides that are equally negative, you're going to cause a repulsion. So there's going to be a repulsion between these two metal leaves, and they're going to try and move away from each other, similar to what we see on this side here. Now, what we know is if we want this to go back down, obviously we need to release the electrons. So we want these electrons to go away. Okay. Now we can do it in two ways. You can use normal visible light. So according to the old classical physics, if you just use visible light and you shine onto the piece of metal, if you have enough time, that visible light should have enough energy accumulated onto this piece of metal and make these electrons disappear. That's not the case though. What we actually find is no matter how long you expose the visible light onto a piece of metal, it doesn't have enough energy to move these electrons out. However, if you used UV light and you shined it on, you actually do see electrons getting displaced and these metal leaves coming back towards each other because it's losing all that negative charge into the atmosphere. So that's one idea of what we see in the photoelectric effect. It's that the type of wave, so the type the type of wavelength of light would affect the displacement of electrons. So that's an interesting and really big find there. We have a little simulation, and we're going to go back and forth with this simulation here to really depict what we're going to talk about with these follow-up experiments. So the next person we'll look at is J.J. Thompson, and his idea is very simple. Okay. Before we go on though, let me just quickly define a couple of things. So say we have this little terminal here. This is going to be my negative terminal. This is going to be my positive terminal. I'm going to call the negative terminal my cathode. That's where I'll be expecting electrons to be emitted. And this will be my anode, where I believe, or where the electrons should be going to. Now, J.J. Thompson's experiment was very simple. You have UV light that shines onto the surface of a piece of metal, and he realized that there were an injection of electrons. How did he know that? Because on his galvanometer, he registered a current. Okay. The electrons that come out from this cathode, we coin them photoelectrons because they have been emitted by photons. So electrons that have been ejected from photons. When these are in the circuit and we get an electric current, we call this the photoelectric current. Something along those sorts there. Okay? So that's one thing there. So let's have a look. Our first little demonstration is what we have here. Okay? We have visible light, or red light here, visible light here, and we're shining it onto a piece of sodium. Okay? As you can see, there is no electrons being emitted at this point here. If I drag it along and go to a shorter wavelength, okay, so shorter wavelengths has a greater energy. We'll talk about why exactly that in a second. I'll take it to a shorter wavelength, and you see I get electrons being emitted. So this is the demonstration of the photoelectric effect. When I have enough energy in the photons, I'm able to eject electrons from the metal surface. So that was the very first observation. Obviously, where the electrons are coming out, that is my cathode. Where they're traveling to is my anode. And you can see I have a current of that value there. So that's the value we have so far. That's a demonstration of J.J. Thompson's experiment there. Okay, now let's go back. Then we have another person. His name is called Philip von Leonard. And he wanted to know if the energy of the photoelectrons would vary if you manipulated the intensity of light. Remember what we said before, okay? The higher the amplitude of a wave was associated with its intensity. In the old classical wave model, that would mean that it has more kinetic energy. So he was trying to investigate that. So he had a variable resistor that tried to oppose the flow of the electrons. So why are we doing that? Now the idea is, if you eject these electrons out, okay, they're going to have some kind of kinetic energy. If you have a resistor, okay, you're trying to oppose the moving electrons. So the electrons are going in this particular direction. I'm going to use a resistor. My resistor is going to try and force it to go in this direction. How am I going to do that? Essentially, what's happening is the current that you inject into this into this circuit will try and force the electrons to go backwards. Okay. Now, if the electron does have more energy, okay, so if it has a high kinetic energy, that means you need a high resistance to push it back. So that's what he was trying to look at. And he found some really interesting things. Now, the actual resistance or voltage applied, okay, is called the stopping voltage. So the amount of energy used, or electrical energy, potential difference that you use to force these electrons to go backwards, we call that the stopping voltage. That's how much potential difference you need to put into the circuit in order to push those electrons back. Okay, so let's just quick definition. Stopping voltage is the voltage required to stop the flow of photoelectrons. So the very point where our net current is 0. Okay, and what he found was if you increase the intensity of light, you will increase the current, assuming that the electrons have been emitted, but the stopping voltage stays the same. So what we can say is the intensity of light, so the intensity of light is not proportional to the current that we see. Have a look here. And then he did change in frequency. So by changing the frequency, he found that the stopping voltage actually increased. So that's an interesting observation as well. And also, increasing frequency does not affect the current. So frequency is not proportional to current, but frequency is proportional to the stopping voltage required. Okay, so that's quite interesting. So let's have a look with our simulation here. So I'm going to test out intensity. Okay, down here at the bottom here, there is on the left, there is a thing called photon density, which essentially means the amount of photons you need, or how much photons you have going through and striking the piece of metal. Now, the voltage we have here is actually the stopping voltage. So let's just show you how stopping voltage works. If I increase the voltage of my system, it's not responding. Let's try and drag it. Here we go. So you can see that once I apply voltage, you can see that the electrons are now slowing down and they're moving backwards. Okay, so we've essentially done, what we've done here is this terminal here is exerting a negative charge on the side. That's repelling the motion of these electrons and pushing it backwards. So the very first initial value of voltage that I put in, that causes the ammeter to go to 0. That's the amount of voltage I need to prevent the current. So in this case, around about 0.3-ish, around that spot there. Could be smaller. So that's the stopping voltage of the sodium here. Okay. If you have a look, if I increase the overall intensity, then you'll find that these electrons will have more energy, and so the stopping voltage would also have to increase. As you can see, as soon as I changed the wavelength, the ammeter registered a much higher value, which means that I also have to apply a greater stopping voltage. Okay, so the thing that you want to use to stop these electrons from moving is stopping voltage. To increase that stopping voltage, you increase the frequency or decrease the wavelength of the light. We do say frequency for a reason. I'll explain a bit later on. Okay, so that's what we have here. Now, the next thing we're talking about is the magnitude of our current. So if I change the frequency or wavelength of my photon, you can see that there is no change in the overall current value here. Okay, there's no change at all. But they are moving faster out. Okay, so there is more kinetic energy. We can see that in comparison to 350 nanometers to 526 nanometers. They're definitely going slower with a larger wavelength and a lower frequency. If I increase the photons, so increase my intensity, you can see that there is an increase in the current. Why is that the case? Well, what's actually happening here is if you think of light as individual packets of energy, and if you have a greater quantity, so greater intensity of those individual particle packets, obviously there's more photons hitting that piece of metal. Okay, so if you have more photons hitting that piece of metal, you're going to have enough energy transferring to each individual electron to then be displaced and leave and go to this side. Okay, so that's what we're looking at here. So let me put that in simple terms again to summarize. Assuming that the electrons have been emitted, if you double the intensity of the light, so you double the amount of photons striking the piece of metal, you'll increase the overall current because you're emitting more electrons. So number of electrons, you essentially increase the photoelectric current. Okay, there won't be a change in kinetic energy if I'm trying to change the intensity of light. Okay, the only way the kinetic energy of the electrons will be changed is if I change the frequency of the photons I use, and that is if I increase frequency, then I'm increasing the kinetic energy of the electrons coming out of the piece of metal. Okay, so to illustrate it nicely here, if you have, let's say, red light coming through, striking a piece of metal, no change. If you have green light striking the piece of metal here, you'll displace these electrons. Okay, if you strike it with a wavelength with a even higher frequency, so it was just enough, let's say it's just enough, okay, high enough frequency, it'll gain even more kinetic energy here. So this is what we're going to try and term the frequency just required to make these electrons get displaced from the piece of metal. We're going to call that the threshold frequency. That's the amount that needs to be used, or the photon needs to be at, in order to get these electrons to move away from the piece of metal or displaced. If you go beyond what's required, then all that gets transferred into the kinetic energy of these electrons. The actual formula we can show is given as F or E equals HF. But we'll talk about that in a bit more. Okay, so let's quickly look at what is the issue with the current wave model and the photoelectric effect. So the idea is the wave model would predict if you have electrons, or electrons will be emitted so long as the intensity of the light is higher. What you did see is no matter how high the intensity of light I used, there was no electrons being emitted. So let's just quickly go back. So let's just try and decrease the overall intensity. Okay. And let's decrease or increase the wavelength. So no electrons coming out. I'm going to increase the density of photons. So I'm going to increase the amount of photons I have. You can see there's way more photons striking the piece of metal. Nothing's coming out, so there's no photoelectric effect occurring here. Okay, the wave model says over enough period of time, if I have enough intensity of light, so enough light striking it, then I should get electrons being displaced. That's not true. The photoelectric or the wave model also says that the current size depends on the intensity and frequency. We already proved that no, it's only intensity. Frequency doesn't really matter in the context of the size of the current that we have. We also said that if we have low intensity, all the metal needs to do is absorb more energy, and over a period of time, there will be electrons that get emitted, but at a delayed instant. What we did see in that simulation is there is no time delay. As soon as there is enough energy of that particular photon absorbed, the electron will come out, and you'll produce a current in the circuits, assuming that it's connected into a circuit. And we also said that, or the wave model also stated that the kinetic energy should be related to intensity of the wave. If you recall, that's what we talked about with like those surfing waves. But we found that the overall maximum kinetic energy the electrons have is related to the frequency of the photons shining on the piece of metal and not on the intensity of light you use. So that's a quick summary of what we have. So prolonged exposure of light at high intensity will displace electrons. That's what the wave model states. That's not true. If you pass a particular threshold frequency, then you will get electrons being displaced from the piece of metal. And there's also no time delay when these electrons are displaced from the piece of metal. It also states, the wave model that is, that the photoelectric current is dependent on the intensity and frequency of light you use. We know that's not true. Intensity is the only thing that's directly proportional to the amount of photoelectric current you produce. And kinetic energy of the electrons is dependent on the intensity of light. That's not true again. What we see from the photoelectric effect is that only frequency matters when it comes to the overall kinetic energy of your photoelectron. So there's that. That's some additional information for you to read at. We'll go over a bit more later on. But the formula that really explains the photoelectric effect, let's just write it down here. So what we actually know is each photon, the way that Max Planck used to explain this, is each photon is just a packet of quantized energy. So E equals hf, h is Planck's constant, f is the frequency of light you used, okay? And our idea is if f is f naught, so threshold frequency greater, then you will get a displacement of the photoelectric effect. I'll end it here today when it comes to the investigations used to show the inconsistencies of the photoelectric effect with the wave model, and how this kind of shows that light does act more like a particle in this particular instance than a wave. In the next segment, we're going to talk about how the photoelectric effect and the kinetic energy of the electrons being emitted is an example of the law of conservation of energy. So until the next video comes out, please stay safe, revise thoroughly, and see you next time.